بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. Today's subject is going to be the compact heat exchangers, and the compact heat exchanger will be the materials of this topic is from the book of Kakash, chapter 10, and also from the book of compact heat exchanger by Case and London. The contents of this presentation will be as follows. First, we start with the introduction. Then we'll talk about tube fin heat exchangers, and then after that plate fin heat exchanger. These are the two types of compact heat exchangers. After that, we will talk about surface data from the book of Case and London. Rating of a plate heat exchanger will be next, to see the procedure and the calculations needed to do the rating of plate fin compact heat exchangers. After that, we are going to see some salt examples on compact heat exchangers, and finally we will shed some light on sizing compact heat exchangers. المواضيع حقت المبادلات الحرارية المكتظة أو المضغوطة هي نوعين. النوع الأولاني اللي هو تيوب فين، والثاني اللي هو بليت فين. وحناخذ المعلومات من الكتاب حق كيس اند لندن، وبعدين نتكلم على الريتنج سواء بالنسبة لبليت فين أو تيوب فين، ومع الإكزامبلز اللي موجودة في شابتر 10 من كتاب كاكاش، بالإضافة إلى في الأخير نتكلم عن السايزنج procedure to size a compact heat exchanger. As an introductions, actually that there are mainly two types of compact heat exchangers. The tube fin, where you have a tube and fins. The tube can be circular or the tube can be flat, and the tubes themselves, the fins, I'm sorry, they can be either continuous like this one and this one, or it can be circular fin on tubes and circular tube as this one. The second part is, or the second type of compact heat exchanger is the plate fin heat exchanger, where we have gas-to-gas heat exchanger. This is, for example, side 1 gas, and this is, for example, side 2 of another gas. One of them is hot and the other one is cold, and side 1 passes through these spacing, and the other side is passed through the other spacing in a cross-flow arrangement, so that the heat exchange can take place between the hot fluid and cold fluid. ممكن يكون في عندك أكثر من pass زي الرسمة هذه. مثلا في عندنا more than one pass, so that this is one pass going from one end of the heat exchanger to the other end, and then go back and so forth. But both this one and this one, all they have gas-to-gas heat exchanger, what we call the plate fin heat exchanger. The heat exchanger actually is the compactness of the compact heat exchanger is measured by what we call alpha, where alpha is actually the ratio of the heat transfer area divided by the volume. So whenever this value of the heat transfer area divided by the volume is greater than 700, around 700, the compact heat exchanger is called compact. So this is alpha equals to 700, greater than 700 square meter divided by cubic meters. There are other heat exchangers that are not classified as compact heat exchangers, since alpha is less than 700. This is another figure, shows also the same thing. In the lower scale here there is an alpha which is has a variation, increases as this way, and then we have a hydraulic diameter on the upper scale, where as you see, as the alpha increases, the hydraulic diameter decreases. Again, you can look into the tubes in the heat exchanger. You can see that as the tubes increases in numbers, you see that the compactness, you arrive to compactness. Again, alpha can be calculated for certain geometries, and certain heat exchanger, they are not classified as compact, but as you can see here gas turbine for example rotary regenerator are compact heat exchanger يعني مبادلات حرارية مكتظة لأنه الألفا حقتها اللي هي الريشيو حق الماء الاريا divided by the volume is greater than 700. This is another view showing the basic idea of gas to gas heat exchanger and liquid to gas heat exchanger. So liquid to gas heat exchanger, what we call tube fin heat exchanger. This is an example of it where you have tubes, circular tube with this continuous fin, and gas to gas heat exchanger you have two sides. This is side 1 for example for the gas that is going in this direction, and the other direction is going for example this way. This is for example gas 2 or side 2 that also goes in this areas, whereas this one side 1 is goes in the other plate spacing. The plate spacing actually is called B1, which is the distance for the flow to enter into the heat exchanger. This is B1 and this is B2, and in general actually according to the types of the fins, this is what we call a triangular fin, and the distance here between the plates is B and the thickness of the plate is A. Now we'll go into detail about the tube fin compact heat exchanger. As we said before, we could have either continuous fins or circular fins, and the tubes can be, as we said before, also either circular tubes or flat tubes. This is a figure shows several types of non-circular tubes with continuous fin. Each one of those surfaces, as they are defined in the book of Case in London, they have a designated number. So they call it, for example, surface 9.1.737-S with certain geometrical values that indicate this type of surface. We have several surfaces with different geometries that are available in Case in London, where we have very important figure that gives you the variation of the friction coefficient and the J factor, which is we called Colbrand modulus. So you have two curves. One of them gives you the Fs value, and the other one is give you the Colbrand modulus value. So whenever you have the Reynolds number calculated, you can get the JH, and also you can get the friction coefficient for the calculation of the heat transfer and the pressure drop. كل السيرفيسز هذه اللي موجودة عندك، الاسطح اللي موجودة في كتاب كيس ان لندن، كل واحد له يعني certain geometrical values, and also for each figure we have, for each surface they have this figure that gives you the two important factors, اللي هو ال JH وال FC. In order to calculate the tube fins, of course now we are focusing on tube fin compact heat exchanger. If you would like to calculate the overall heat transfer coefficient, then you have to add all the resistances, for example the internal resistance, the external resistance, convection, and then two resistances for fouling inside and outside, in addition to the resistance in the wall. Of course, since we are talking about tube fin, so inside the tube there is no fins, but outside there is a fin, so you have to calculate what we call the overall surface efficiency eta 0, which is a function of the efficiency of the fin in addition to omega, where omega is the ratio of the area of the fin divided by the total heat transfer area. So in order to calculate the U value for the designing of a compact heat exchanger, or even performance of a compact heat exchanger, you need to calculate all these parameters. The main thing that is in addition to what we have said before is this value, is what we call the heat transfer coefficient for the outside, for the gas side. Of course, as we said before, eta F is the fin efficiency. Generally, HI, which is the heat transfer coefficient for the internal flow inside the pipe, can be calculated from the correlations for flow inside a pipe or tubes. And H0, which is for the gas side, then we have to use K and lambdas, as we said before, the figure that we indicated just a while ago, that gives you the friction coefficient and give you the J factor, from which you can calculate the H value. So HI is very well known for heat transfer inside tubes, and H0 is the heat transfer coefficient for the gas side that has to be used, has to be calculated using K's and lambda figures and tables. There are certain definitions that I'd like to shed some light on them. The frontal area is called AFR. The minimum flow area is A minimum. Sometimes we call it AFF to indicate free flow area. If you divide the free flow area divided by the frontal area, you get what we call sigma, which is dimensionless, meter square by meter square. Also, we have alpha, as we said before, which is defined as the heat transfer area divided by the volume. If you take a very simple tube fin compact heat exchanger, where you have tubes with circular fins, liquid is going into the tubes, and you have the gas side, and you have three dimensions, LT, LP, and LL. So it is very we have to use the following notations in order to do some calculations. For example, the gas side, there is the omega. Actually, some of the definitions, omega is defined as the fin area divided by heat transfer area, which is AF divided by A, and the hydraulic diameter is very well known that it is 4 times the cross-section area divided by the perimeter. If you multiply this equation by L and divide by L, you get what we call the area here, and then you have 4 AF F, which is free flow area multiplied by L. This correlation is going to be, or the relation is going to be used later when we talk about the rating or sizing of compact heat exchanger. If you take L divided by H from this equation, if you take L divided by DH, then you get the ratio, the length of the gas side divided by the hydraulic diameter will be equal to the area, the heat transfer area, divided by 4 multiplied by AF. For this configuration, where we have a tube fin compact heat exchanger, the gas side frontal area is LP times LT. This is what we call frontal area for the gas side. For the liquid side, the frontal area is LL multiplied by LT. So you have the frontal area for the gas side and the frontal area for the liquid side. Another parameter that we would like also to define here and use later, maybe we have defined it before actually, is G, where G is equal to the density multiplied by the velocity maximum. Of course, G is going to be used for the calculation of Reynolds number. Actually, Reynolds number for calculation in the compact heat exchanger is going to be G multiplied by the hydraulic diameter divided by the viscosity. We said that G is equal to the velocity maximum multiplied by the density. So once you multiply G, which is rho multiplied by the velocity, multiplied by the hydraulic diameter divided by the viscosity, you get Reynolds number. That is very fundamental in order to get friction coefficient and the J factor. Other definitions that also we are going to be used for the calculations for the tube fin heat exchanger, what we call the Colburn modulus JH, which is defined as a Stanton number multiplied by Prandtl number 2/3, and Reynolds number, as we said before, G times DH divided by the viscosity. Stanton number actually is Nusselt divided by Reynolds and Prandtl, which can be written as the heat transfer coefficient divided by Cp multiplied by G. From this equation we can find H, the heat transfer coefficient, as a function of JH, Colburn modulus, multiplied by Cp, the specific heat, G, the mass velocity, Prandtl number to 2/3. So this means that once you get the value of JH from K's and London or other sources, you multiply it by these three parameters, you get heat transfer coefficient for the gas side. The mass velocity, as we said, is going to be rho multiplied by V maximum, but also it can be written as rho V multiplied by the frontal area, which is the mass flow rate, divided by AFF which is equal to m dot. This is multiplying the three parameter give you the mass flow rate, be divided by the free flow area, and the free flow area can be related to the frontal area by sigma. So frontal area, free flow area is equal to sigma multiplied by frontal area. The pressure drop, major pressure drop, which is due to the friction, is, as we taken from fluid mechanics, it's going to be 4 multiplied by the friction coefficient multiplied by L over D, and then multiplied by the kinetic energy, which is rho v square over 2. You can convert this equation into G, because the velocity multiplied by the density is G. So finally you can calculate the pressure drop due to the friction in the wall using this equation. Of course, we are going to take L over dH here and substitute, as we said in the last figure, in the last slide. Fc actually is going to be used as a friction coefficient, and L over dH actually we found in the previous slide that is going to be equal the area, the heat transfer area, divided by 4 multiplied by the area, the free minimum flow area or the free flow area. So you can actually take L over dH from this equation for the pressure drop and write that delta B is going to be friction coefficient, heat transfer area divided by the free flow area, G squared divided by 2 rho. If you would like to consider other sources for the pressure drop other than the friction, this is for the friction, which is, as we said, if you multiply this one by this one, you get the same equation that in the previous slide. This is another term for the pressure drop due to what we call acceleration deceleration, which is function for sigma and multiply also function for the density at inlet and density at outlet. All these parameters have been defined before. The A is for the heat transfer area, AFR is the frontal area, AFF is the free area, and the density is actually at inlet and outlet, and the mean value also. You can actually take the area of the heat transfer area divided by the free flow area and substitute that, since you know that alpha is equal to the heat transfer area divided by the volume. So actually you can take the heat transfer area and say that it is going to be alpha multiplied by the volume. The free flow area is going to be the sigma multiplied by A frontal. So that's why actually we need these two parameters in addition to the omega also, which is the free the fin area divided by heat transfer area. So that we have to understand these parameters and how they are related to in heat transfer and pressure drop. I am going to show you some of the information about the surfaces for the tube fin surfaces, tube fin compact heat exchangers from the book of Case and London. This is one type of surface, which is a circular fin and circular tube. The surface designation is as you can see here, CF-7.0-5 and for all figures that we are going to see, either for tube fin or plate fin, we are going to see that in the x-axis we have Reynolds number, and in the y-axis we have two parameters. We have the friction coefficient for this for example for this surface, this one, and other parameter which is JH. Also you have this curve. So this is a general idea about how these information, how Case and London put the information for the surfaces, different surfaces. So you have to understand the following. You have to understand that in most cases, in all cases تقريبا, you have a curve, two curves that shows the variation of friction coefficient and the J factor with Reynolds number. In addition to that, you will find several parameters defined for that certain surface that has certain designation. So for this surface designation, all the parameters that are for this surface, for example, the fin diameter, the outside diameter of the tube, the fin thickness and the fin materials, and the fin area divided by the total area are also given. For example, here the tube side outside diameter is given, the fin pitch the flow passages, the hydraulic diameter, which this is actually the hydraulic diameter, this is the hydraulic radius, but the 4 times the hydraulic radius will give you the hydraulic diameter. Fin thickness, free area over frontal area, which is sigma, and also the heat transfer area divided by the volume alpha, and in addition to omega, which is the fin area divided by the total area. This is as we said for certain surface which is designated by certain letters and numbers, which is CF dash 7.7 dash 5.8. I'm sorry, this is should be 7.7 dash 5 over HJ surface. This is also the same thing, the same surface, but the data is taken from the book of the chapter 6 of the book of Incorpora. Chapter 11, I'm sorry, 6th edition of the Incorpora, which is the same data but only in English units. The same thing actually for the alpha, sigma, and omega. This is another surface. This is a continuous fin with circular pipe. The surface designation is 8-38T as indicated here. The same thing about Reynolds number and the two parameters that we said before, so that you know that almost all the compact heat exchangers have the same idea of presenting the friction coefficient and J factor as a function of Reynolds number. This is the third, no, I'm sorry, this is the same thing, but this is taken from Incorpora 6th edition, chapter 11. You will find the example there that we have also talked about when we talked about heat exchangers long time ago. The same idea, sigma, alpha, omega, the dimensions are here written in English, SI units, but maybe you will find it in English units in the book of Case and London. This is the third surface. This surface is CF 8.72. The same thing about what we said before, the three very important parameters, the friction coefficient and J factor as a function of Reynolds number, in addition to the data about the surface itself. But here is different, since we are talking about circular fin and circular pipe. This is another figure, surface. This surface is 9.1.737S, which is, as you see, it's a flat tube with continuous fins, and the same idea that shows the variation of the two parameters, the friction and the heat transfer. In our book, in our textbook, of Kakaj, this figure is from chapter 10, which shows again the two important parameters, J factor and the friction coefficient as a function of Reynolds number, but to show you the variation for different surfaces, here in the book the author shows several surfaces, variation of these figures here for JH, for FC, I'm sorry, and these groups of figures for the J factor. This is just show you that the variation of J factor and FC factor with Reynolds number for different surfaces. I'm sorry. Again, we talked about the overall heat transfer coefficient, as we said before. Here we indicated how to calculate the resistance in the wall. If you neglect the fouling, you'll get this equation. One thing that you have to remember is that in evaluating the overall heat transfer coefficient, for example, using this equation, we need to calculate, as we said before, the heat transfer coefficient using Case and London figures, and also the surface overall surface efficiency. This is the resistance of the wall. Of course, we are neglecting a fouling here, and here the heat transfer coefficient inside the tube. And AI divided by A0 is the ratio of the heat transfer area inside the tubes and the heat transfer area in the gas side. So we need to calculate this one. Actually, this is one of the key parameter that has to be calculated in order to find the overall heat transfer coefficient. This is the same thing actually. You can write since you need this ratio and this ratio. So next we are going to do some calculation to find the ratio of the heat transfer area inside and outside. One of the idea to calculate the ratio of the heat transfer area inside the tube and the heat transfer outside the tube. Of course, outside the tube we have the fins, and here we no fins. So this is no fins inside the. But here outside we have the fins. So we would like to calculate the area here, the area inside, the heat transfer area inside, and the area outside. So we would like to calculate how much is A inside, A outside, or A outside divided by A inside. One way to do that is that if the thickness of the pipe is known, so you have the diameter inside is known and the diameter outside is known, the heat transfer area inside is very well known, which is the perimeter multiplied by the length of the heat exchanger or the tube. And the outside area, we are going to do the following. If we consider the outside area without the fins, we call it AOP to indicate this is the heat transfer area without fins. And then we can divide A inside by A outside without fins as D over D0, since L will go with L and pi will go to pi. So we have now a ratio of the heat transfer area divided by the outside heat transfer area without fins. Now from this equation we can write that the heat transfer area is equal to the ratio D inside over D outside multiplied by A0P or OP. Now we know that the heat transfer area outside here and outside is going to be the area of the fin plus the area of unfinned part. What we are going to say is that the area of unfinned part is the same as the outside heat transfer area without fins, as if we are neglecting the area taken by the fins on the surface. So the area taken by the fins is neglected. So what we say that is the area of the heat transfer area of the gas side with fins equal the area of unfinned, which is going to be, this one is going to be AOP, the heat transfer area for the outside surface without fins, plus A fins. From this, actually, we can write that, of course, this is what I said before, this is neglecting the area occupied by the fin. So the area of the unfinned part is going to be A0P or AOP, which is the heat transfer area without the fins. From which we can say that from this equation, we can write the AOP is going to be A0 minus AF, where A0 is the total heat transfer area minus AF. Now take AOP and put it in this equation. Substitute it back in this equation. So you get A inside divided by A out is going to be DI over D0, and then AOP is going to be A0 minus AF, but we all defined by A0, so we will have A inside divided by A outside, which is the heat transfer area that we are looking for, the heat transfer area for the internal flow and the heat transfer area for the outside flow is going to be D inside D outside multiplied by one minus A fin divided by A0. Of course, A fin divided by AF by A0 is going to be omega, which is a parameter that is known in the data for that particular surface. Notice that what we did here actually is we said this is equal to D inside by D outside multiplied by AOP is going to be taken from this equation, so it's going to be A0 minus A fin. Now if you divide this equation by A0, so you get AI divided by A0 is going to be D inside divided by D outside, and then it's going to be 1 because you are dividing both sides by A0 minus AF divided by A0, which is this equation. So basically there is a trick to find the heat transfer area inside the tube divided by the heat transfer area for the gas side, by assuming that the area occupied by the fin is very negligible on the outer surface, from which actually you can get this equation, which says that the area, heat transfer area inside divided by the heat transfer area outside is equal to the diameter ratio multiplied by this parameter, which is 1 minus omega, where omega is the fin area divided by the outside area. This will help us to go back in the equations that I showed you just a while ago, in this equation, to insert A inside over A outside with the correlations that we found a while ago. In order to understand the situation for the tube fin and plate fin heat exchangers, actually what we did before from the book of Incropera in chapter 11, we talked about compact heat exchangers, but only for tube fin compact heat exchanger. There was an example which is very illustrative and very good to understand. Example 11.6. Of course, we are talking about Incropera 6th edition, not the 7th edition. In the 6th edition, actually is taking a compact heat exchanger, liquid to gas, circular tube, circular fin, and then made the calculations. You have to go back to this example in order to understand it very well and resolve it, so that you go and understand the next step, which is the sizing of tube fin compact heat exchanger. We are going to go quickly through this example just to understand what we have done before, and then we will continue after that. The example says that you have to consider a fin tube compact heat exchanger with a core configuration of 11.6 in that book. The core is fabricated from aluminum, and the tube has an inside diameter of 13.8. In the waste recovery application, water flow through the tubes provided inside heat transfer coefficient HI equals 1500. This is the heat transfer coefficient inside the tube, while combustion gases at 1 atmosphere and 825 Kelvin are in cross flow over the tube. If the gas flow rate is 1.25 kilogram per second and the frontal area is 0.2 square meter, what is the gas side heat transfer coefficient? So H0 is needed, and if the water flow rate is 1 kilogram per second, is to be heated from 290 to 370, what is the required heat transfer volume? So he's talking about the volume now of the heat exchanger. How much is the volume and how much is the heat transfer coefficient for the gas side? Of course, what we have this configuration. We have a tube and we have a fin. So this is the fin, and inside this there is a water with a heat transfer coefficient, as we said before, 1500 watt per meter square Kelvin, and the surface actually is known. The surface designation is CF 7-5 over 8J, which is a circular fin or circular tube. The flow rate of the gases, the combustion gases, is with the mass flow rate is 1.25 kilogram per second, while the temperature entrance is 825. The frontal area is 0.2 square meter. In addition to this, he said he gave also another information. He said that the flow rate of water is given 1 kilogram per second, with entering temperature is to be heated from 290 Kelvin to 370 Kelvin. So when we go back to this solved example in Incropera 6th edition, you find the solution explained fully with step by step in order to get the heat transfer coefficient H0 and the volume of this heat exchanger to fulfill the need, which is heating the water from 290 Kelvin to 370 Kelvin. This is just to indicate that this is the surface that we are talking about, and we are talking about Incropera 6th edition example 11.6. The procedure that was followed in that example is illustrated here. We are not going through this because we have taken it before. The only thing that we would like now to make a revision and build on that. So what you have to do in this example, for heating the water from 290 degrees to 370, and all the information that is given for this surface, HI, actually the heat transfer coefficient for the internal flow is given, which is 1500. So there is no problem with that. Since the front area is known, sigma is going to be found from the surface that we are given, we can calculate G, and we can also calculate the Reynolds number, from which we can get JH from the figure, indicated figure for that surface, and also we can get H0. So this is the first required from this example to find the heat transfer coefficient H0. The basic idea is to get G and get Reynolds number, go to the figure that is for the same figure that we have here in this example, you get J, and from J you can get H0. In order to calculate the volume, because the volume is needed in this example, we have to get the overall heat transfer coefficient. So first of all we have to find the fin efficiency, and also we have to find also eta 0, which is the overall surface efficiency. Once you get that, and since H inside is known, H outside is known now, in addition to eta 0 is known, you go back and use the relations or the equation for finding U0 and find how much is the U0. After that, you can, since the water is entering at 290 degrees and leaving at 370, you can find Q. And Q max also can be found, because Q max, as we know, is going to be equal C minimum times delta T max. So Q is known and Q max is known. Divide Q by Q max, you get what we call the effectiveness. So we have the effectiveness. Since we know the overall heat transfer coefficient, we can calculate NTU. All of us know that NTU equal to UA divided by C minimum. Of course, we are talking about U0 based on our outside area. So you enter the figure or use the equation for a cross-flow heat exchanger, and entering with the effectiveness and with CR, and you can get an NTU. So if I draw, for example, a figure like this one, where you have here NTU and you have here effectiveness, and you have several figures for different CR. So CR is known, for example, this figure, and NTU have been calculated. So I'm sorry, the effectiveness has been calculated. So you go from here to here, and then you can get an NTU from this figure, from which you can get from the NTU, actually, since NTU equals U multiplied by U0 A0 over C minimum. C minimum is known, U0 is known, so you can get the heat transfer area. Once you get the heat transfer area, you can find the volume, since alpha, as we said before, alpha is equal to the heat transfer area divided by the volume. So from the figure or the relations, you can get the NTU. You can calculate once the NTU is known. Since this one is known and this one is known, you can get the area, the heat transfer area. Then you can calculate the volume, since alpha, as you said before, is known and A0 has been calculated. You can get the volume of the heat exchanger, from which also you can get the length of the heat exchanger in the direction of the gas, which is going to be, since the volume is going to be the frontal area times L, so L is going to be the volume divided by the frontal area. I would like just to, you can calculate also the number of tubes, rows in the direction of the flow. Let me show you, but just if you consider that we have something like this, and this is tubes with fins, and we are suppose that the gas side is going this way. This is the gas, and of course inside the tube you have the liquid. Okay, now you can draw it like this, but I can also we can draw it like this, so in order to understand the dimensions. So this is the gas is entering this direction, gas, and as we said before, this is the direction of the liquid going inside. Okay, the frontal area is given. The frontal area, A frontal, is given. I think it is 0.2 square meter. Okay, And we have calculated A0, which is the heat transfer area outside, gas side. Okay, and we used alpha equal to the area divided by the volume to get the volume. So the volume is known, since alpha is known. Once you get the volume, we know that the volume equal to the A frontal times L liquid. This is liquid, I'm sorry. Here, this L is the length of the heat exchanger in the direction of the flow. So once you calculated the volume and you know the frontal area, you can see that you can calculate the length of the heat exchanger in the direction of the flow. You divided the volume by A frontal area. Once you get the frontal area, once you get the length, actually you can calculate how many tubes in these directions. So if you example, if this is the flow, this is the gas going outside, you can calculate how many rows of tubes in the direction of the gas side. Okay, so the rating of a tube fin heat exchanger is the process itself is explained in this slide. Basically, it is from example 11.6 from Incropera, the 6th edition. The solved example is very clear, but it is very important in order to understand how to rate tube fin compact heat exchangers. There were two requirements for this example: the heat transfer coefficient H0 and the volume of the heat exchanger in order to fulfill certain duty. In the book of Incropera, the 6th edition, additionally that the number of rows in the direction of the gas has been calculated. Of course, this can be done since if L is known of the heat exchanger, then the number of rows can be found using NL equals to the length of the heat exchanger in the direction of the flow minus the diameter of the fin divided by the distance SL, which is the center to center distance between the tubes, plus one. So if you have an arrangement, as we said, for example, circular tube, circular fins, these are tubes surrounded by circular fins, and if the distance from here to here is SL, and the dimensions of the flow of the gas is going this way, gas is L, and the diameter of the fin is dF, then you can use this above equation where L is the total distance of in the gas side minus the fin diameter divided by SL, which is the center to center along the direction of the flow, plus 1 will give you the number of rows in the direction of the